I noticed that some of you have your textbook tonight, Civil Engineering Reference Manual. I see them laying out there. Most of you have that manual with you tonight?
Yes. Looks like it.
We're going to talk about engineering economics, and there's a couple of things in the reference book that I wanted to point out to you. At the end of the chapter on engineering economy, there's a set of tables. If you'll turn to page 226 in your reference manual, if you have it, you'll see a table that looks something like this. And I picked the 4% table. And when you get ready to work these problems, I think before you go to the exam, you need to decide whether you're going to work these problems by using the tables or using a calculator. And you can do either one. And either approach would work. But the equations are given on table 2.1 on page 2.3 of the textbook. And I have some transparencies. I'll show those similar to that. I'll show those same equations in a few minutes. I suggest that you learn how to, if you're going to use those tables or the equations in your calculator, I would suggest that you practice on some really simple problems. These tables are presented in slightly different ways in different textbooks. I would guess that most of you had some kind of a course in engineering economics, and you probably, if you had it very many years ago, you probably used tables. If the format of the table is slightly different and you use these, you need to practice some really simple problems and be sure that you learn how to use them properly. The chapter on engineering economics in here is a good chapter. I think you could probably use it for preparation of the exam. You should be in pretty good shape. I gave you about 70 pages, which I unfortunately numbered after I gave your copy to be mailed to you. So you've got 70 some odd pages that aren't numbered. I went through and numbered them later, and I'll be referring to those numbers. You may leave them in a stack, and we'll just go through that stack, and you'll have to count off as we go through. One of the I've taught engineering economics several years, and some of the really common mistakes that people make, that students make when they solve these problems, is they misuse the formulas, or they don't pay attention to what the formulas are for the solution of very specific problems. Those tables are for the solution of very specific problems. I would like to, if you'll turn to, I believe this was probably the first page of the material that I sent you. It shows a summary of equations and cash flow diagrams, and the entire page looks something like that. I'm going to zoom in and look at that one of the diagrams down. I'm going to look at this diagram right here. Have you found that page in your handout?
Yes, it's the first page.
Okay. Now there's right. Okay, good. It was supposed to be the first. I was hoping it was the first page, not the last page. There's a diagram, a sketch like this in your textbook just before the tables. The last page in the chapter, just before the tables, there's a figure like this, and it's probably a little more clear. But in any event, let's look at that. Let's look at those at these sketches. Here's the one I want to look at here first. Is let's say this one right here. We have a P is a present value. We have a uniform series of you know, A could be annual payments. In this case, if these are annual payments, then this would be 0 time, and this would be the first year, the second year, the end of the third year, end of the fourth year, end of the fifth year. And And so we could have on this kind, if we were solving this problem, we could have a present worth and be looking for an equivalent annual payment over 5 years at an interest of, say, 6%. While the interest may be 6% for that 1 year, when you plug interest in the equations that are given, you'd normally plug in 0.06. But you'd want to be sure and check. If you're using some equations, you'd want to check that and be sure that you plug in the ratio rather than the percent. I have seen the equations published where you plug in the percent rather than the ratio. And that's just something you want to check before you go in, take the exam. Now then, you'll notice on this diagram that there's no A value right here. Now, suppose that the statement of the problem said that you were going to put an annual payment. Let's say this A value was $100 a year, and you're going to put the annual payment in right now. And then you're going to put an annual payment at the end of each year of $100. Well, then you would have to solve this problem, and you wanted the present worth, let's say. We're talking about this problem here. Well, what is the present worth of a $100 payment at t equals 0? It's $100. So you'd solve that separate. If they put an A value here, you would find its present worth. Its present worth of that payment is equal to whatever it is. If it's a $100 payment, the present worth is $100. Then you'd find the present worth of all of these others and add them up. But the equation will not solve a problem with a payment here. It's set up for all the payments being at the end of the year. It's going to blur a little bit, but I'm moving up here. The same thing for the one above, where we have a future value. F is a future value. Here's some annual payments. Again, I'm going to put in a value, $A. This wouldn't have to be dollars. This could be people. It could be population, dollars, whatever. It could be gravel, depending on the statement of the problem. But in this case, I'm depositing, or I have a deposit of $100 at the end of this interest period, $100 at the end of this one, $100 into this one, $100 into here, $100 there. What's the future value? Well, of course, if the interest was zero, I guess if the interest was zero, it'd be equal to the sum of all those $100. But if we have interest, if I is not zero, then F is going to be larger than the sum if it's a positive interest. If it's a negative interest, which it could be a loss of some kind, it could be a negative interest. Again, if someone put a value here, then you'd break this down into two problems. You'd solve this problem by this equation, and then I'm going to go up to the sketch above, and now you have one value here, and I'd get its future value. So I do that in two parts. So what you have is some very simple, basic sketches that are applicable to the equations, or the equations are applicable to those sketches. What you're going to do is take an exam, and they're going to state some problems that more than likely will be a little different than those classical solutions. So what you'll have to do is piece these things together. You may have a single payment, or you're not expecting one. The only place that this really give you any difficulty is in a gradient. I want to go back to that sketch and go down to the one that's labeled F over G. Okay, and you notice here's 0, here's 1, 2, 3, 4, and 5, and they have a gradient, and the first gradient starts at the second year. And you want to remember that. Typically, if you had a gradient problem, the value, in other words, if you had a gradient, it would normally be on top of a uniform series. So you can have an A payment of, say, $100 a year, and that $100 a year is increasing $20 a year. Let's say that this gradient is equal to 20, and let's say this A is equal to 100. So what I've got is I'm simulating $100 every year here, and the gradient, it's increasing 120. So the first year I've got $100, the second year I have 120, the third year I have 140, fourth year I have 160, and the fifth year I'd have 180. for that reason, you leave the first one blank. You know, that's the way they chose to do it. So when you draw this sketch, don't forget that the gradient starts with the second at the end of the second year. The uniform series starts at the end of the first year, and that's a real common mistake. It's a real common mistake that people make. And so I would suggest that you look over those sketches, look over that sketch that comes at the end of the chapter. So at the end of the chapter, you would find this, and I'll zoom out on it, and that shows the sketches, okay? And then behind that, you would find these tables. Now then, what I urged students to do that don't solve these problems very often, but they want to be able to come back a year or so after they take the course, what I encourage them to do is to draw the sketch that's appropriate for each one of these columns in the table. And they give it to you on the previous page. Just sketch it on the table. That way, if you don't, if you're not solving a lot of engineering economics problems, you won't forget what the free body diagram looks like for the equation. You just got to, if you're going to use the equation or use the table, you've got to remember what the free body diagram looks like. Okay. Now then, you know, we have about 45 minutes or so to cover engineering economics, and that's a little quick. I pointed out that you need to learn to either use the equations or to use the tables. Now then, going back to those sketches, normally you're either given the annual series and you want to know the present value of that annual series, or you're given the annual series and you want the future value of it, or you're given a future value and you want the present value, or vice versa. You may have a gradient. Normally these equations are set up as if n was given and as if the interest value is given, and then either A or P or F or G is given, and then you want to find one unknown. And but occasionally in these problems, you've got the present value, let's say, and the future value, but you want to find n, okay? Or you've got the present value and the future value, and you want to find the interest. Now there's two general ways you can go about solving that. One general way would be to manipulate the equation so that you could solve for n or r directly. The other way to do it is to do it by trial and error. Now if you're going to do a trial and error solution, it's probably faster and easier to do it by using the table. So use of the table is a pretty handy thing to do, a fairly practical thing to do. And on this exam, I don't think they would penalize you because you use the table rather than using a calculator. It's practical to use the calculator if you have a programmable calculator. If you're going to solve these problems just punching in the equations, that would be a little slow, especially if you made a trial and error solution.
Are we allowed to use a calculator on the exam? Take in two calculators, one that specifically is an economics calculator with all these programs already in it, with the little card on it that shows what function does each thing?
Yeah, I believe so. As long as it doesn't make a racket when it prints or something like that, and as long as it doesn't have a hard disk wherein you might copy the problems down and take them home with you and sell them for more money than you'll make as an engineer, then they don't mind.
Okay, thank you.
Always, as a matter of policy, though, when you walk in there, if you have any questions, I would ask the examiner.
Okay.
Yeah.
See, gee, I'd kind of take the other attitude. I would walk in with it on my hip like a gun and dare anybody to look at it.
Yeah. Yeah.
Because I mean, if it's a calculator, it's a calculator. I don't think they have a complaint.
I think they have the obligation to tell you what you can't use.
Yeah, right. And all it says is silent calculators and no hard disks.
Yeah.
That's about the only thing I read in what you can't take. So you can't take a little laptop. You'll never make it in with that. That's a little too big.
Okay, now then, let's look at the, let's just go through the problems and look on, I have it numbered at page 3, and I'm not sure whether that number is correct. That one might have gotten a little out of order. Did you find this sketch in your handout? It shows a correct value, a correct sketch for the equivalent future value F from a series of uniform periodic payments. It shows an incorrect sketch. And the second one is incorrect because it has this first value of A. And this one is incorrect because he forgot to put this last value of A. That doesn't mean you can't solve this problem. What that means is you can't solve these two problems using those equations or tables that are given in the book directly. You can use them indirectly. For example, you could find on this one, you could find the future value here for this. That would be one you could solve. Now then, if you want the future value here 1 year later, you could take that as a present value now, and you could find the future value 1 year from now. And that's how you'd tackle that problem. Okay, let's go on and look on page, it's about page 4, and it's example problem 3.1. And it says, aiming to replace their mainframe computer 5 years from now, a firm of consulting engineers is depositing $10,000 per year in an investment fund, earning interest compounded at 10% annually. Find the balance of the fund, including deposits and accumulated interest at the end of 5 years. So we've got this sketch. What we've got is we know A, we want to find F. We would use this equation to find it, and it's just a direct solution. We could also use the table, and it's one that you could solve directly. I don't think you have any trouble following that. You might have trouble finding an engineering firm that could afford to put $10,000 a year into an account drawing interest. Skip up page 5 and go on to page 6, which is example problem 3.3. Now this shows there's the example, but I'm going to zoom down here, and this sheet's pretty handy, but they made a little typographical error in it, and so I'm going to zoom in where the error is. They wrote this equation twice. Here's an equation they wrote, and they put this parenthesis is in the right place, this parenthesis is in the wrong place. It belongs there. Okay. Down here, they put the parenthesis in the right place, the last one, but they put the first one in the wrong place. It goes there. Now what they did here is, in order to solve for the n, what they want to do is find the life. Now you could find this life by using a table and just try 1 year, try 2 years, try 3 years, or whatever. I would normally start with a short life and then a long life and bracket it and come in. But you can solve for n directly by taking the logarithm of all the terms in this equation, then you can solve for n. And that's what they did. They just took this equation, took the logarithm of all the terms in there. They did a little rearranging before they did it. And then you can solve for n directly. And so that might be something that would be worth remembering or writing down, although I think I would solve that problem if I was solving it on an exam like this. I think I would solve it by trial and error. Now then, how would you know when you had a good solution? How would you know?
I don't know. How would you know?
Yeah, how would you know? What you do is you're solving. If you guess n is 1 year, F is supposed to come out $1 million. If you guessed 1 year, F would come out less than $1 million. You haven't got enough money. In this case, if you guessed 10 years, the answer came out 8. If you guessed 10 years, you would have more than $1 million. That's too long, and so you would do it until you got the answer that you're looking for. In this case, you know both A and F. And so you know when you, by trial and error, you know when it comes out because you have an answer that agrees with the known answer. Okay, that was, go to page 7, which is example 3.8a, and I just wanted to point out a couple of things to you there. On some of the problems, they talk about PTZ, which is problem times 0. Sometimes people use strange nomenclature. PTZ is problem times 0. ETZ is equation times 0. On those equations and those figures that I showed you, there's a times 0. Sometimes the problem times 0 is different than the equation times 0, and you just need to take that into account. And they've got a problem there, example 3.8a, which is simple and straightforward. You can go through it. I'm going to try to go through this material fairly fast. There's some things in it that we'll stop and work. Go to page 8, which is example problem 3.8. This is a negative interest rate. And so in this case, he says a new retirement community will need a second unit to a new water treatment plant when the population reaches 40,000. But this is a new retirement center, so right now the population is 0. And so the population is increasing 6,000 new residents per year, with an estimated birth rate of 8 per 1,000 and a death rate of 14 per 1,000, resulting in a negative annual increase of 0.6%. How long will it be before the second unit is needed for the new water treatment plant? So you got a negative birth rate, but you got people moving in, and you got a population of 0 at the beginning. So here's your 0 time, and so this would be one that you could solve directly by using the equation, by solving for n. You could also, and in this case, he got the equation completely right. He didn't make a mistake on the equation. So you could solve for n. It turned out to be 6.8 years. You could also do that one by trial and error. The next problem on page 9, though, is probably the one that would be, and that's dealing with population rather than dollars. Okay, let's go on there. On page 10, there's example problem 7.4, capitalized cost. Now, the capitalized cost is a term that there's two popular, I guess you could say, two popular meanings of capitalized cost. And I went one page too far. Go back one page, and let's look at what we mean by capitalized cost. And it says capitalized cost has two popular meanings. Accountants use capitalized cost to describe expenditures that may be depreciated over more than 1 year. So there you take all of the costs into account over the time period, as contrasted to expenditures that may be written off, expensed entirely in the year they were made. The second meaning for capitalized cost is found in the traditional literature of engineering economy, and this, generally speaking, is what they mean on the exam, but not always. Here, capitalized cost refers to the equivalent lump sum amount required to purchase and maintain a project in perpetuity. The net present worth for n equals infinity. And so let's look at an example problem, and that would be example. The first one is example 7.4. Find the annual cost of maintaining a certain right-of-way is $10,000. So it costs $10,000 a year to maintain this right-of-way, and find the capitalized cost with the interest of 8%. Well, the solution, finding capitalized cost, means find the present worth with n equals infinity. And so you would do that by the capitalized cost is 10,000 divided by the interest rate. If you look in the table, or if you plugged in an equation and put a large number, if you put a number above about 60 or 70 years, the factor would come out as 0.08. And so you just divide the annual cost by the interest, and what that would say is that if you put $125,000 in an account and it was drawing 8% interest every year, you would be able to make that $10,000 payment. And so they give you a mental picture there. The mental picture of funds could be invested at 8%. How much should be invested so that the interest alone would pay for the right-of-way maintenance? And the answer is $125,000. Note that where lives are comparatively long, the capitalized cost closely approximates the present worth. And he used 100 years instead of infinity, and it came out was that $60 off. So well, normally we would just use the interest. Any long life, we would say it was into perpetuity. Okay. On page about page 13, there's a problem, example problem 8.8, involving finding the. You have an annual series and finding the gradient, and again, we got a 100-unit university merit housing project. Is expected to incur the following costs and income. What annual income is required for this project to break even? That would be a kind of a typical problem. So you're going to have to come up with some kind of an equivalent cost. You're going to have to, you got a new cost of $1 million. You got maintenance costs of $100,000 a year, increasing $2,000 a year. You got a major overhaul every 10 years for $200,000. You got a salvage value at the end of the 40 years of $100,000. Somehow you've got to compare these, and you could do this by bringing everything back to a present value. You could convert everything to an equivalent annual cost, or you could work with in this case, you could come up with you're trying to find an annual income. On this particular solution, he found the net annual worth. He found what the annual cost was. So you've got a new cost of $1 million, and does anyone see what the life of this thing? Yeah, the 40-year life. We're doing this over 40 years. So what you've got is a new cost of $1 million, and so you convert that to an annual series with a life of 40 years and an interest of 6%, and you would find then that the annual cost is $66,500. You've got the maintenance cost, which is $100,000, so it's already done. Then you've got the maintenance gradient, and you'd have to you have an annual gradient, and you have to get the an equivalent annual cost. And that comes out to be $24,720. Which is on the next page. I'm sorry. I saw it. I guess I've got to put it on the screen so you can see it. And so in this case, we would convert the gradient to an annual cost. We take the major innovation, and how often we're doing that major innovation? It was every 10 years, right? Major overhaul of $200,000 every 10 years. So you can convert that to an annual series, but the life here is 10 years. Interest still 6%. And then you add all of these up to get the annual income required for break even would be the sum of all those costs. Okay.